Introduction. Welcome to this comprehensive video on fluid dynamics. In this session, we will explore the fascinating world of fluid mechanics, a field that studies the behavior of fluids, including liquids and gases, at rest and in motion. Whether you are a student, a researcher, or simply curious about how fluids behave in nature and engineering applications, this video will provide you with a foundational understanding of key concepts and principles. Fluid dynamics is not only crucial in fields such as aerospace, civil engineering, and environmental science, but it also impacts our daily lives in ways we often don't realize. From the flow of water in rivers to the movement of air around airplanes, the principles we discuss today help explain these phenomena. Let's dive into the key topics of fluid dynamics, starting with fluid properties and moving through the various theories and principles that govern fluid behavior. Section 1. Fluid properties. Before diving into the complex world of fluid motion, it's essential to understand the basic properties that define fluids. Fluids are substances that continuously deform under an applied stress, and these properties significantly influence their behavior. The density of a fluid is a measure of how much mass is contained in a given volume. For example, water has a density of about 1,000 kilograms per cubic meter, while air has a much lower density. The viscosity of a fluid indicates its resistance to flow. For instance, honey has high viscosity, meaning it flows slowly, while water has low viscosity, flowing easily. Next, we have surface tension, which is the force that causes the surface of a liquid to contract and resist external forces. This property is why small insects can walk on water or why a water droplet forms a spherical shape. Lastly, we discuss compressibility. This refers to how a fluid's volume changes in response to pressure. Gases are highly compressible, meaning their volume decreases significantly with pressure. Liquids, on the other hand, are generally incompressible, meaning their volume remains almost constant under pressure. Section 2. Hydrostatics, fluids at rest. Now that we've covered fluid properties, let's focus on hydrostatics, which deals with fluids at rest. The fundamental principle here is Pascal's law, which states that any change in pressure applied to an enclosed fluid is transmitted undiminished throughout the fluid. This explains how hydraulic systems, such as car brakes or lifts, work. The pressure in a fluid at rest increases with depth. This pressure can be calculated by multiplying the fluid's density by the gravitational acceleration and the depth of the fluid. In simpler terms, the deeper you go in a fluid, the higher the pressure you'll experience. We also have Archimedes' principle, which states that any object submerged in a fluid experiences an upward buoyant force equal to the weight of the displaced fluid. This explains why objects float or sink in water. For example, a boat floats on water because the buoyant force equals the weight of the boat. Section 3. Hydrodynamics, fluids in motion. Hydrodynamics studies the behavior of fluids in motion. One of the key principles in this field is Bernoulli's principle, which describes the relationship between pressure, velocity, and elevation in a moving fluid. It states that as the velocity of a fluid increases, the pressure exerted by the fluid decreases. This principle is why airplanes can generate lift. The faster moving air over the wings results in lower pressure above the wing, lifting the plane. Another important concept is the continuity equation, which asserts that the mass flow rate of a fluid is constant along a streamline. This means that when a fluid flows through a pipe that narrows, its velocity must increase to maintain the same flow rate. In addition to Bernoulli's principle, we also consider Navier-Stokes equations, which describe the motion of fluid substances. These equations take into account factors like viscosity, velocity, and pressure and are used to model complex fluid systems. However, solving these equations is challenging due to their nonlinear nature. Section 4. Flow types. In fluid dynamics, flow can be classified into different types based on how the fluid moves. Steady flow refers to a situation where the fluid's velocity at any given point remains constant over time. In contrast, Unsteady flow occurs when the fluid's velocity changes with time. Laminar flow is smooth and orderly, where fluid particles move in parallel layers with minimal mixing. This occurs at low velocities or when fluids are highly viscous. Turbulent flow, on the other hand, is chaotic, with eddies and vortices forming as the fluid moves at higher velocities or when the fluid is less viscous. The transition from laminar to turbulent flow can be predicted by the Reynolds number, a dimensionless quantity. When the Reynolds number exceeds a certain value, the flow becomes turbulent. Section 5. Applications of fluid dynamics. Fluid dynamics is essential in a wide variety of applications. In aerospace engineering, it helps design efficient aircraft by optimizing the flow of air over the wings, minimizing drag, and maximizing lift. In civil engineering, fluid dynamics is used to design dams, water treatment plants, and pipelines, ensuring efficient fluid transport. In the automotive industry, the principles of fluid dynamics are applied to improve fuel efficiency and reduce drag on vehicles. Marine engineering also relies heavily on fluid dynamics to design ships and submarines that can withstand the pressures of deep-sea environments. Section 6. Advanced topics in fluid dynamics. As we move into more advanced fluid dynamics, we encounter phenomena like shock waves and cavitation. Shock waves occur when a fluid moves faster than the speed of sound, creating sudden pressure changes. This can be seen in supersonic aircraft or during explosions. Cavitation happens when the pressure in a fluid drops below its vapor pressure, leading to the formation of vapor bubbles. These bubbles can cause damage to machinery such as propellers or pumps when they collapse. Conclusion. In conclusion, fluid dynamics is a vast and fascinating field that touches almost every aspect of modern technology and natural processes. From the study of fluid properties like density, viscosity, and surface tension to understanding how fluids behave at rest and in motion, fluid dynamics helps us solve critical problems in engineering, medicine, and the environment. By exploring fundamental principles such as Pascal's law, Bernoulli's principle, and the continuity equation, we gain insights into the behavior of fluids in different situations. Whether dealing with slow-moving water in rivers or high-speed air over an aircraft wing, the study of fluid dynamics is essential for designing and optimizing systems across a wide range of industries. Thank you for joining us in this exploration of fluid dynamics. We hope this video has provided you with a clearer understanding of the key concepts and applications in this exciting field.